All right, welcome. Today we are diving deep into a super critical challenge for any team building with AI. How do you optimize your vector databases and knowledge bases to make them truly enterprise ready?
Okay, let's get right into it. A lot of engineering teams, they start with a pretty simple retrieval augmented generation, or RAG setup. And it looks great in a demo, right? But then it just hits a wall when you throw the complex demands of a real world production environment at it. So, what's really going on here? Well, the core problem is this tension between two different types of search. On one hand, you have semantic search. It uses dense vectors, and it's fantastic for understanding meaning and context. But on the other, you need lexical search for finding exact keywords. A real production system has to have both, because while semantic search gets the vibe of what you're asking, it could totally miss a specific tax form, like 1099 MISC or some critical error code.
And this brings us to what I think is the most crucial takeaway. Every single architectural decision you make is a trade-off. You are constantly in this balancing act between three competing priorities: the accuracy of your results, the total cost of the system, and you should be thinking cost per query here, and of course, the latency your users feel. The thing is, you can't max out all three at once. You have to make very deliberate choices.
So we're going to walk you through this whole optimization journey, starting from the foundational choices all the way to a production-ready stack. We'll frame our decisions using that optimization triangle, then we'll dive into choosing the right embedding model, optimizing your vector database, which is really the engine of this whole thing, and finally, we'll cover advanced retrieval and re-ranking to make sure what you deliver is not just fast, but actually correct. All right, let's get into our first section and see how this all builds up, starting with what is, arguably the most fundamental choice you're going to make, your embedding model. This is the absolute foundation of your entire RAG pipeline. Okay, so right out of the gate, you've got this big strategic choice, and it has direct impacts on your cost and latency. Are you going to go with open source models? You get total control, total data privacy, but you have to accept the infrastructure overhead. Or do you go for the convenience of proprietary APIs, where you pay per token, but you get to offload all the management? Look, there's no single right answer here. It's all about what your team prioritizes: cost, control, or security.
Now, this is where it gets really interesting, because this slide just completely demolishes the whole bigger is better myth. You might assume more parameters means better performance, right? But that's not the whole story. These benchmarks show that a really compact model like E5 Small is 7 times faster than the much, much larger Qwen model. Just think about what that does to your end-to-end latency and your compute bill.
So how do you get the best of both worlds? Well, there's this really powerful technique you should look for called Matryoshka Representation Learning, or MRL. It's a super clever way to embed your data. You can think of it like a Russian nesting doll, but for vectors. And here's the magic of it. MRL lets you take one big, high-dimensional embedding and basically chop it down to a smaller size with almost no performance loss. This means you can dynamically tune your vector dimensions, slashing storage and memory costs by up to 99%. It lets you perfectly hit your specific targets for that accuracy versus cost per query trade-off. Okay, so we've got our data represented as these high-quality vectors. Now we have to optimize the engine that actually powers the search, the vector database itself. Your first big decision here is all about architecture. A purpose-built database like a Pinecone or a Milvus is optimized for absolutely massive scale. But an extension like pgvector lets you unify vectors with your existing relational data, and that can dramatically cut down on complexity and operational costs. A few years ago, this wasn't even a contest. But today, these extensions are incredibly competitive for workloads under 100 million vectors, offering a really compelling low-cost, low-complexity alternative. But as your data scales up into the billions of vectors, a huge new problem emerges. Traditional CPU-based indexing becomes this crippling bottleneck. It could potentially take your system offline for days. So the question is, how do you solve that? The answer, it turns out, is GPU acceleration. By offloading all these intense vector calculations to GPUs, the results are, well, they're staggering. This recent benchmark from OpenSearch shows exactly how dramatic that difference is across indexing time, total cost, and throughput. And here's the headline number: a 9.3 times improvement in indexing speed. A process that used to be a multi-day ordeal can now get done in just a few hours. That's not just an improvement, it's a total game changer.
And here's the part that might seem a little counterintuitive. Even though GPU instances are more expensive per hour, the massive speed increase means you use them for way less time.
So the net result is a 3.75 times reduction in your total operational cost. So you get faster and cheaper. I mean, that's a massive win. Okay, one last trick up our sleeve for the database itself, quantization. This technique basically compresses your vectors, say from 32-bit floats down to 8-bit integers. This directly cuts your memory usage by 75%, a huge cost saving, with what is often a negligible impact on your retrieval accuracy. It's one of the best bangs for your buck you can get in this whole process.
All right, our core engine is finely tuned. Now let's move up the stack and focus on refining the retrieval strategy itself. This is where we go from just finding good enough documents to finding the perfect answer.
A production-grade RAG system isn't just one step. It's really a multi-stage pipeline, and it's designed to maximize precision while managing that latency. So first, you retrieve a broad set of candidates using a hybrid of semantic and keyword search. Then you fuse those results together, but the crucial third step is re-ranking, where a more powerful and yes, more expensive model rescores those candidates. Only then do you send the absolute best 3 to 5 documents to the LLM. This filtering is so key to reducing your token costs and getting a much better final answer.
And the good news is you've got great options for that re-ranking step. You can use a managed API like Cohere for top-tier accuracy and just ease of use, or you could self-host a high-performance open-source model like Mixspread, which really shines on complex data types like code. The choice, again, comes down to your budget, your latency requirements, and how much infrastructure you're willing to manage.
Okay, let's put all the pieces together. We get the individual components, but how do you choose the right combination to build a full production stack that actually meets your specific enterprise needs?
So which one is for you? Well, the right database really depends on your workload. For general RAG, a hybrid search leader like Weaviate is a fantastic choice because you get that sub-100 millisecond query performance. But if your team already runs on PostgreSQL, the simplicity and cost-effectiveness of pgvector is just incredibly compelling. You're trading some of the specialized features for a massive reduction in operational complexity. And this is probably the most important thing to remember. Don't just pick whatever is on top of some generic leaderboard. The best tool is the one that fits your constraints, your data, your query patterns, and your team's operational reality. Always benchmark with your own workload to understand the true cost per query and latency for you. And this brings us right back to our optimization triangle. You've seen the trade-offs at every single layer of the stack. So the final question is for you and your team. For your next project, which of these will you deliberately sacrifice for performance? Will it be cost, complexity, or control? The right answer isn't what's on a slide. It's what makes your project actually succeed.